Okay, so let's get started. In the last class, we looked at these Chernoff type bounds. Basically, we derived the general Kramer-Chernoff bound, uh, which in many cases allows you to derive an exponential tail bound on the probability that x is greater than or equal to mu plus delta, or x is less than or equal to mu minus delta. All right. So you can separately derive bounds for the right tail as well as the left tail. And we proved this, again a very simple application of Markov's inequality. And although I didn't prove it, this is a homework exercise. If you have a sequence of n IID Bernoulli P random variables, then we can derive a tail bound on the probability. So recall that an is the sample average of x1 through xn. So we'll use the notation an is equal to 1 by n times summation xi. So the probability that this deviates from the mean p by an amount delta times p. Remember that this additional tolerance is delta times p can be upper bounded by some constant times e to the power of minus n times delta square p by 3. Right? This is not the tightest possible bound that you can derive. You could derive something that's a little more tight, but it will be a more complicated function in terms of delta and n and p and so on. So this is this is not the best possible bound, but it's a good enough bound that we can use in many applications. Okay, and in the last class, we saw one particular application for load balancing. So in an example where, sort of almost a toy example, where you have n servers and m jobs, and each job is independently and uniformly allotted one particular server. We showed using these Chernoff bounds that the probability that the maximum load exceeds the average load, which is 1 by n if the number of jobs is exactly equal to n, probability that the maximum load for any server exceeds, say, 1 plus log n, decays as 1 over n. All right? So with very high probability, the maximum load for any particular server is going to be at most 1 plus log n. All right? So this Chernoff bounding technique gives you this, and it turns out that if you do uniform allocation, you can't really do too much better. You could potentially, by using a slightly tighter Chernoff bound, you could improve this to log n by log n, but that's not so much of an improvement. On the other hand, as I briefly alluded to, there are other approaches you can use, perhaps not a uniform allocation, but there are other techniques where you can improve this log n to log n. But that does not involve purely random or uniformly random allocation. All right. So in today's class, we'll first see another example or another application of Chernoff bounds, in particular to bound the performance of supervised learning algorithms. So we'll start with a binary classification problem, in general an Emery classification problem. So the classification problem is the following. So we have some ground truth. And our goal is to learn this ground truth, or try to get an estimate of what this ground truth is by observing data. Right? For example, what is the ground truth in a classification problem? So as an application, you would think of you have an image and you want to identify whether this image contains a car or not. Right? That's an example of a classification problem. Or it could be that you are given an arbitrary sample of text, maybe some word, and you want to design or classify this into, let's say you want to identify if this is a verb, you want to design an algorithm which, given a word, identifies whether it's a verb or a noun or an adjective or not. All right. So those are examples of classification problems. So at the very beginning, we want to develop a mathematical model for this classification problem. Right? So the classification algorithm or the ground truth, there is some kind of an input. Right? We'll call this variable x, and this input is drawn from some set. We know what the set is. All right, and this input in the example of image classification, so this could be an image or document or whatever, depending on the applications, the input that is going to be fed to the so-called classifier. All right, and what we want to know is, for each document, unknown to us, perhaps, there is a label. So, for instance, this in the example of classifying images, the label could be, there is a car in this image, there is no car in this image. Or if you are given, let's say, a piece of text, maybe a word, whether this is a noun or verb or adjective, and so on. For example, if you wanted to design a spam filter, the input X could be an email, let's say, and the class or the label for each email is, this is spam, this is not spam. Okay, so just a little bit of terminology. So these Y's are going to be called labels, and X are commonly called features. Our goal is to, now we need some kind of a model to represent this particular ground truth. Okay, what is the relationship between the feature and the label? So one could assume that y is some function of x. So if you look at all possible emails in the universe, there is some way of mapping each email to a particular label, whether it's spam or not spam. We don't know what this label is, but there is some underlying ground truth, right? So if we could say that the ground truth, there is some sort of function f which takes every email and outputs whether this is spam or not. Okay. But more generally, you could also assume that there is some joint distribution between x and y. Okay. So firstly, when I say that for every email, you have some function which tells you whether this is spam or not, I also need some other way of representing how these emails are drawn. Right? So when you want to design your spam filter, you don't get an arbitrary email. You assume that the emails are drawn according to some distribution. The email that you get to your algorithm come according to some distribution. This distribution is not known to you. Okay, that's the most important. So X could be drawn according to some distribution, which is unknown. Or more generally, X and Y are jointly distributed according to some distribution Pxy, which is unknown. Note that this subsumes this, so the first case is a special case of the second one, because you could just define this joint distribution to be Px times Py given x, and this Py given x could be 1 if y is equal to f of x and 0 otherwise. That would contain this particular case. All right, hopefully that's okay. Okay, so this is what I'll call the data distribution. So this data distribution is unknown. What we have access to design our classification algorithm, our goal is to come up with some function g which takes as input one of the features and outputs a label. Okay, so we'll assume that y is the set of all possible labels. Now, this is known beforehand. And hopefully this g is a good enough approximation for f, or at least performs well over completely random data. I'll make this a little more precise as we go along. Okay, but how do we design G? It is based on some data set or samples, which is just a collection of so we are given n samples, and we'll make some assumption on these samples. We'll assume that these samples are all independent and identically distributed, and they all follow the data distribution. The data distribution is unknown, but this data set or the set of n samples is given to us. Using these n samples, we are free to come up with any algorithm we like, and the algorithm is going to be this function g. All right. And we'll assume that this function g is not anything arbitrary. We'll assume that this function g comes from some collection of functions. All right. So we'll draw it from this class of functions. So from this class of functions, our goal is to choose that function which best approximates the data in some sense, or in other words, gives us the best possible performance if we see a random sample. In the case of classification, right, suppose that we have designed some particular G. What do you think is a good measure of performance? So again, let's assume that you use this data set, you have designed a G. And our goal is to design this G so that it performs well on a completely new sample. So you're drawing a new sample X, and you want to know how well the algorithm, the classifier, works on this new sample. The output of the classifier is going to be G of X. So specific to this classification problem, what do you think is one way of measuring the performance of a classifier?
Binary classifier.
Okay, something a lot more simple. Accuracy, and how do you define the accuracy? There's only one sample.
Simple indicator variable now. She's value is same as the data.
So it's just the probability that you make a mistake, right? So what is the probability that G of X is not equal to the true label Y? So that's one measure of performance. In general, I could look at a different measure of performance, as you guys have suggested. But at least let's keep things very simple for the moment. The measure of performance will be what is the probability that my classifier makes a mistake? Because we know what the ground truth is, right? The ground truth is x comma y drawn according to pxy. And my goal is to design a G such that this probability of misclassification is as small as possible. So the goal is to design G such that probability that G of x is not equal to y is small. Okay, this statement is okay, right? But we have a problem. Right? If we knew what pxy is, then choosing such a G is straightforward because we know the class of all functions where we can choose G from. We know the joint distribution pxy. You just evaluate this probability of misclassification for each G and choose the best G from this class. But I don't know pxy. Right? I only am given a set of samples. Right? I'm only given the data set S. And this set S consists of n samples. But what we know is that all of these samples are drawn from the same distribution pxy. Right? So now I need to, I've said that design G such that this probability is small, right? But how small can we make this? How small do you think we can make this? Can we make this 0? Maybe not. And why do you think we can't make it 0? What are the fundamental bottlenecks to making this? There is noise. As I said, we're drawing it from the same distribution, right? So what do you think is the problem?
Data set need not represent the probability distribution.
True, but I'm assuming that it's drawn from the same distribution. If it's not drawn from the same distribution,
Low probability events.
true. What could happen is, for whatever reason, my data set is not, because after all it's a realization of n IID samples, right? And this realization could potentially deviate from pxy, from the true distribution pxy, because it is just random samples, right? That's one thing that could happen. Or maybe I don't have enough samples to get a good approximation of pxy. That could happen. Anything else?
I think for the limited data set that we have, it could be part of many different distributions.
We are assuming that it is drawn from the same distribution. That's a fundamental assumption that we are going to make.
So maybe the samples that we are choosing might be, let's say there is a Gaussian curve and we are trying to pick samples more on the narrower part rather than the center.
Sure, that's what I said, that the samples that you see may not be a good realization. Right? But so that's something to do with the data set. What else?
The functional conceit may not be good enough.
Correct. So basically I'm saying that I draw G from some class of functions. Now, beforehand I don't know what is a good class of functions. Right? So whatever I do, I'm limited by this class of functions G. And I can possibly, the best that I can do is what the best G could do. Right? So the best that I could possibly perform is minimum overall G in the class this is the best that I can possibly ever achieve. Right? No matter what I do, it is impossible to design an algorithm that does better than this. Right? Hopefully that much is clear. And let's assume that the one that achieves the minimum probability of error or probability of misclassification, let's call it G star. Okay. So hopefully we should be able to design an algorithm given these samples that give the output of this algorithm should hopefully be G star or something that performs almost as well as G star. Right? That's the goal. Right? Any questions? Great. So it turns out that for a given class of functions G, doing this may or may not be possible. It may or may not be possible to achieve or get G star or something close to G star all the time. So let's formalize this. So this is going to be formalized using the following approach, which is called the pack learning approach. Probably approximately correct. Right? Because as you see, there are two things. So one is G star. So firstly, G star may not achieve zero misclassification error. That's one thing, because fundamentally we want to evaluate the performance on a completely random sample. Right? And the other thing is we are designing the algorithm based on a random data set, n IID samples. So obviously you can't get G star or close to G star all the time. Right? With some probability you are going to get something that is very different from G star. It's bound to happen. So we'll say that the end goal is going to be to design some algorithm, let's call it G hat, which gives me the following guarantee. So there are two things. One is the classifier. We want to output the classifier. But how we choose the classifier from this data set is totally up to us. All right. So our learning algorithm basically will consist of some way. If I give you a data set, you have to tell me how you are going to choose G from this class that does well. And let's say that from this, based on this learning algorithm, you output some G. Right? Let's define R of G to be the probability that G of X is not equal to 1. All right? So we'll call this the risk that is achieved by the classifier G. Okay, so this is the risk that is achieved by G. What we'll try to guarantee is, okay, before that, so a learning algorithm is some rule that takes the data set as input. Right, so given a data set, you output some G hat S. Okay, maybe this G hat S is the solution to some optimization problem, all right, or whatever. So for given these samples, you output one classifier. So the rule according to which you get a classifier from these data samples is going to be our learning algorithm. What is a natural algorithm to consider? In fact, some of you even hinted it earlier. So given n IID samples, someone gives you a labeled data set, how would you choose G? Right? What is the most natural way of choosing a G?
By overfitting.
You're jumping way ahead, but how would you choose G?
The map from X to Y in the data set.
I know, but how do you choose the G? Right? For example, I could have a number of classifiers, right?
So
Which classifier do you choose?
Minimize the loss.
Minimize?
The loss.
How do you define the loss? Again, my end goal is to minimize this particular risk, right? But remember, I don't know what is the value of the risk, because the definition of this risk depends on the distribution. I don't know the distribution. All I have are IID samples.
So we put the data points that is available with us,
Okay?
and then we see that whether our particular function is matching to the y output or not. If it's not matching, then we eliminate those functions in the set of functions which are giving incorrect.
But maybe the data set that I have, every function G makes at least one mistake. That could happen, right? As I said, I don't guarantee that there is a function G that achieves zero risk.
Maybe minimum number of misclassifications.
All right. So one way is I choose that G which makes the minimum number of errors on this particular data set. So that's one choice or one particular learning algorithm. Right? So G hat S could be let me take the fraction of misclassified points. All right. Okay, and this one subscript G of xi not equal to yi, this is equal to 1 if G of xi is not equal to yi and 0 otherwise. Okay, that's the indicator variable, which is equal to 1 if whatever this happens, and it's equal to 0 if this does not happen. Okay, and this particular algorithm is called the empirical risk minimizer.
If I define the same loss as number of misclassification and use I-tag algorithm like gradient descent, is it same like empirical risk minimization?
Not necessary. So there are two things that you're doing, right? So firstly, a couple of things to keep in mind. When I say empirical risk minimization, I'm saying that I want to minimize this exactly. Okay, if I don't allow approximate minimizers of this particular quantity. So typically, when let's say you train a neural network in order to minimize a certain loss, you're not doing the minimization exactly. You're only doing it approximately because you have constraints on computational power, time. Right now, we are going to assume that we don't have any such constraints. I give you all the time in the world to design your training algorithm, and I give you all the computational power you want to design your training algorithm.
Sir, the data points that we are choosing are also coming with some probability
Correct.
from a distribution.
Correct.
So, sir, we also need to take into account the probability while we are minimizing, a probability across every data.
We can't. We're just given one data set, right? We're given only one data set.
That data set,
It's a random data set. All right. So that's why I'm not guaranteed. So no matter how I design this algorithm, let's say I employ empirical risk minimization. This empirical risk minimizer is going to be different for different realizations of the data set. There could be some realizations of the data set where this does badly. There could be some realizations of the data set where this does extremely well. Okay. So, for example, let's assume that, again, not in this particular context, okay, but in a general estimation problem. Let's suppose you have a coin and you want to learn or estimate the bias of this particular coin. One way of trying to estimate the bias is you toss this coin a number of times, and then fraction of heads is going to be the bias. Okay. Now, with non-zero probability, I could potentially see a sequence of all heads. All right. If n is large, the probability of seeing this sequence could be very small, but it does happen with positive probability. So there is a chance, there is a possibility that I see a sequence of all heads. And my estimator is going to output bias equal to 1 for this particular sequence. Okay. So ultimately, whether you design a good estimate or whether you get a good estimate or not is ultimately tied to the samples that you see. There's no doubt about that. So that is why when we say that we want the learning algorithm to do well, we also have to take into account the randomness in the data set. Okay? So it's not possible to do well all the time. And as you'll see, that's why we say that we want to do pack learning, probably approximately correct. So what does it mean when I say probably approximately correct? Our goal is to achieve, so we want to design an algorithm such that g hat, the probability that r of g hat is greater than or equal to r of g star. The ideal case scenario is when I achieve r of g hat equal to r of g star. If I can do that, then that's ideal, because that is the minimum possible that I can achieve from this class. Right? I can't do any better than r of g star.
sir,
But
the class of like functions is already given to us.
that is given to us. Yes. So we are given this calligraphic G. That is given to us. Okay. And from this calligraphic G, we want to do the best. Okay. So I may be able to achieve r of g star, but it's impossible to achieve r of g star all of the time because my data set is random. So I'll give a small back off from this. Okay, I'm allowed to do slightly worse than r of g star, but not too much worse than r of g star. I want to design an algorithm, I want to get a classifier that is close to r of g star and should be epsilon close to r of g star. But even this, I can't guarantee this all the time. Because as I said, if you are trying to estimate the bias of a coin, with some positive probability, you will see a sequence of all heads. With some positive probability, you will see a sequence of all tails. In both of these cases, you will be doing terribly. because your estimate of the bias would be way off. Similarly, here it's not possible to get R of G star or even close to R of G star all the time. You can only get it with some probability. And we want that the probability that you deviate from R of G star by too much should be small. Okay, so this is going to be our goal. Right? Given some epsilon and delta, I want to design an algorithm such that the excess risk, right? So, or in other words, the probability that the risk that my classifier achieves deviates from the best possible risk by an amount epsilon, the probability that this happens is less than or equal to delta. Okay, and this probability is over the random samples that we see, the data set. All right. So this is evaluated with respect to the data set. With respect to the data set S, but you should keep in mind that these R of G hat and R of G star, they're also probabilities, right? The probability that you make a misclassification error. But these probabilities are evaluated with respect to a new sample which is independent of the data set S, because you've already seen the data set, right? So what you want is to perform well on a new sample, and that's the challenge behind learning. Okay, is this? Yeah. I'm sorry? It is according to the same distribution.
And second question is why can't I use R max of sigma indicator of G of X equals to 1?
You could, but do you think it will make a difference?
But then it's just a convention.
It is just convention, yes. That's true. You could, instead of minimizing this, instead of minimizing misclassification error, I could say I want to maximize the correct detection error, right? But this is convention because it will also allow us to generalize beyond just classification problems. Right? Again, given any minimization problem, you can also pose it as an equivalent maximization problem. It is just that conventionally you look at minimization problems. It's just as I said, as we saw earlier, convex versus concave. As I said, if you have a convex function f, then minus f is concave. So you could either minimize a convex function f, which would be equivalent to maximizing a concave function minus f. All right. And another thing to keep in mind that empirical risk minimization is one particular algorithm. You're free to choose to design any algorithm you wish. So for example, I could say that I want to, instead of minimizing this particular quantity, I may want to minimize this plus some other function of G. Right? And we'll see such algorithms perhaps sometime later in the course. But this is one very basic algorithm that we could just have at the back of our minds. One concrete learning algorithm. Okay, any questions?
So G hat is empirical risk minimization of the functions.
Okay, so I'll say that GS hat is the empirical risk minimizer. So G hat S is the empirical risk minimizer, but this G hat over here could be any general learning algorithm. All right? Given any learning algorithm, this is going to be my goal is to design a learning algorithm that achieves this. Okay. So we'll say that a class of classifiers or a collection of classifiers, this is also going to be called a hypothesis class, is pack learnable if the following happens. So if for every epsilon and delta greater than 0, I should be able to design an algorithm that achieves this using a finite number of samples. Okay. So after all, I need some bound on how many samples do I need in order to achieve a particular epsilon delta accuracy. There exists some n which depends on epsilon, delta, and g, such that there exists a learning algorithm So this learning algorithm takes as input n IID samples, and these n IID samples xn by n, and outputs some g hat with the property that the probability that g hat, sorry, r of g hat is greater than or equal to r of g star plus epsilon should be less than or equal to, less than or equal to delta, as long as the number of samples is at least n epsilon delta g. Right. So, loosely speaking, I should be able to, using a finite number of samples, I should be able to achieve this. And this should happen irrespective of what pxy is.
So if you are trying to find g hat, and then you have to anyway compare it to g star, but then that means you already know g star.
You don't know g star.
Then how do we do this? Then you know if the g hat is optimal.
So that's the point. So even though you don't know what g star is, what I want you to be able to guarantee is that you will get close to g star with a certain probability, of course.
That's the thing, we have to get it close to g star. Then how do we know what is this g star to use?
You don't know what g star is, yes, but still my goal is to design an algorithm that even without knowing g star, I want to guarantee that yes, I will be close to g star.
So the algorithm will always be iterative.
Not necessarily. Any algorithm, right? Okay. So in fact, let's see why we can achieve this. Okay. So we'll make some assumptions, simplifying assumptions at the moment. Okay. So So we'll make some assumptions. Assume. So at the moment, this is just a definition. Okay, a hypothesis class is pack learnable if I can design a learning algorithm that achieves this. A particular hypothesis class may or may not be pack learnable. I don't know. All right. So for now, we'll make the assumption that this G is finite. So my hypothesis class, I have only a finite collection of functions, a finite collection of classifiers. From this, I want to choose the best possible classifier. Okay. What I want to show right now is that I can do this irrespective of the value of epsilon and delta. Using a finite number of samples, I can always achieve this, even without knowing pxy and therefore not knowing what G star is. Okay, and in fact, the algorithm that I will use is empirical risk minimization. Right. So, if under this assumption, how well does empirical risk minimization perform? Okay, and this is where we use our concentration inequalities. Maybe just before we even show that ERM performs well, let's try to develop some intuition to see why we would expect ERM to perform well. All right. So recall what is our goal. So our goal is to design a G hat such that R of G hat, which is the probability that G hat of X is not equal to Y, is small. Correct? But we are given n IID samples. So let me define RS of G hat to be 1 by n summation I equal to 1 to n indicator G hat of xi not equal to yi. Right? I use this, so this is what I'll call the empirical risk. Okay, so what you have to keep in mind is that this quantity is a random quantity. And it depends on the data set S, on the random data set, on the random realization S. Whereas this is a fixed quantity. Right? This is just a number, a non-deterministic quantity. A deterministic quantity. So this is a deterministic quantity that depends on pxy. Again, we don't know pxy, so we can't evaluate R. So this is something that is deterministic, but we can't evaluate because we don't know what pxy is. This is a random quantity, but we can evaluate it because we have access to the data set. But the nice thing is that if n is sufficiently large, we've seen that this should be very close to this particular quantity. Right? In fact, what is expectation of RS? Let's leave the G hat out for now. Let's take any particular function G. What is expectation of RS of G?
R of G.
This is just R of G. You all agree? Okay, good. So therefore, if I take any fixed G, then this quantity is going to be very close to this particular quantity. That's what we're guaranteeing. So therefore there's hope. So essentially what I want to do is I want to find that G which minimizes this particular quantity. But what am I doing? I'm finding that G which minimizes this particular quantity. If n is large, this should be close to this, and therefore whatever minimizes Rs should hopefully also minimize R. Alright? Yeah.
Because from R of G, are we evaluating on a particular point, or like, what exactly are we evaluating the probability?
This probability is over a completely new sample that is independent of the data set. Alright?
Still we are taking only one sample from the data.
Whatever. If you can do it over one sample, then you can also do it for any number of samples. Right? So, in practice, what you would do is you would have a separate training data set and a test data set. Right? Using the training data set, you can find RS of G and try to find that G which minimizes the empirical risk. And then you would want to perform, or you want to know the performance of this classifier that you have designed on a completely new sample. And one way of doing that is to estimate what R of G is using the test data set.
So if you are still sampling from the test data set, it's not deterministic, right?
Which one?
R of G, it's not deterministic, right?
It is not deterministic, but again, in practice, you don't know what the distribution is. Right? So at best, you can estimate what R of G is, and one way of estimating R of G is to do it on an independent test data set. Okay. But the important point is that the test data set and the training data set should be independent. They should be drawn from the same distribution, but they should be statistically independent of each other. That's very important. That is why when you design a learning algorithm, when you train your classifier, you should not even peek at the test data set. Your whole training process should not involve the test data set in any way. Right? Because otherwise, the estimate that you would get using your test data could be completely wrong. It's not a good reflection of the actual test performance. Okay, so now we know that for any given G, this is bound to perform well. And in fact, we can quantify how well or how close RS of G is to R of G. Right? What can we say about probability RS of G greater than or equal to epsilon?
Variance of RS of G.
That's a very loose bound.
Chernoff bond, we can say.
I can use a Chernoff bond, right? I could, of course, use the Chebyshev inequality to get a bound of this, but I think that's too weak. So in this case, what can you say about RS of G? What kind of a quantity is it? What kind of quantities are these?
0 or 1.
Yep, they're all independent and identically distributed Bernoulli random variables. And what is the expectation of this?
By now,
Each is Bernoulli, but what is the Bernoulli parameter P? It's R of G, right? So each of these is a Bernoulli R of G random variable. So I can now use a Chernoff bound. Assuming that epsilon is small enough, what is the bound? So firstly, just to make our lives a little bit easier, I claim that this quantity is less than or equal to probability Rs of G minus R of G is greater than or equal to epsilon times R of G. Why is this true? R of G is always less than or equal to 1. So if this particular quantity is greater than or equal to epsilon times R of G, then it obviously has to be greater than or equal to epsilon. Alright, so this event contains this particular event. Okay, now I can use the multiplicative form of the Chernoff bound that I had earlier. This is less than or equal to 2 times e raised to minus n epsilon square times the expectation divided by 3, assuming that epsilon is less than 1. This is for one particular R of G. Right? Okay. Let me assume that R of G is at least some value m. Right? Then this quantity is less than or equal to 2 e raised to minus n epsilon square divided by 3. In fact, this m is nothing but R of G star. Right? Any questions so far? So this is true for any particular G.
So since exponent it is negative and R is less than equal to, how do we get the second inequality that 2 times exponent of n epsilon square by 3?
So basically, you're right. That's a good point. So this is n epsilon square. There should be a little m. Or if you want, let me just put R of G star. Now this is true for any fixed G. Can I say the same thing about the empirical risk minimizer? Because what do I want to show? So GS hat is my empirical risk minimizer. And I want to know what is the probability that this is greater than or equal to R of G star plus epsilon. Or in other words, is it possible just using this to say that R of GS hat can I get a bound on this particular quantity?
Yes.
What do you think?
Sorry, what exactly is the difference between those two terms?
That's exactly what I'm trying to hint at. What is the difference between what I have over here versus what I have over here? Sorry? There's a modulus here also, right? I'm not talking about G star. So I have fixed a particular G. Okay. So once I fix this particular G, Rs of G is basically, you can represent it as a sum of IID Bernoulli random variables. Okay. Each with mean R of G. Is it true for this particular quantity? Is there some subtlety that we're missing? Yes.
G star belongs to the set of all functions.
So G belongs to the set of all functions. GS hat also belongs to the
G is
set.
a generalization of all the functions that we take into consideration. But G star is the function that is learned by the model.
Okay, so why does that? Remember, GS hat as well as G both belong to the same class. But there's some other difference which you're close.
So GS hat is approximation, like closest that we can get to G star. So the error that GS makes will be higher than G star.
That doesn't matter. It's not what I'm trying to get at.
RS of G hat should be equal to RS of G star.
No, not necessarily. So I'm trying to distinguish between GS hat and G. So in the previous case, what was G? Anything, but anything fixed. Right? Any fixed G. What about this?
It's the empirical risk.
Yeah.
It's the empirical risk minimized,
Correct. And therefore,
which is not depends on this.
which depends on S. Right? GS hat depends on S. So GS hat is a random quantity. Right? So previously, when we wanted to use our Chernoff bound, this Rs of G was a sum of IID Bernoulli random variables and with parameter R of G, which is a fixed quantity. It's a fixed deterministic quantity. But now this GS is not a fixed deterministic function. It is a random function that depends on the n IID samples. So now you can't argue that Rs of GS hat is a sum of IID Bernoulli random variables with parameter GS hat, because R of GS hat itself is a random quantity, right? Because the value of R of GS, this depends on the NIID samples. Whereas in this case, this particular quantity is fixed. It's independent of the NIID samples. All right, so that's why you have to be very careful in using your Chernoff bounds. The Chernoff bound assumes that you have Bernoulli random variables and that Bernoulli parameter is something that is deterministic, that does not depend on the random samples. Whereas here, this explicitly depends on the random samples. So I can't use the Chernoff bound to just claim that this quantity is less than or equal to this particular quantity. Okay? But I can do something else. So that's why we'll use a slightly different approach. It's not possible to derive a bound on this directly, but what I can do is the following. What is the probability that R of G or Rs of G minus R of G is greater than or equal to epsilon for some function G? Suppose I wanted to derive a bound on this particular quantity. Yeah? Yep, I could just use the union bound, right? Because this is nothing but the probability union correct? Now I can use the union bound to say this is less than or equal to summation over all G in G probability greater than or equal to epsilon, which from my Chernoff bound previously, I can bound this by size of G times 2 times e to the minus n epsilon square R of G star by 3. Correct? So basically, if the good event now that I'm considering is that Rs of G is epsilon close to R of G for every single G. Okay. So suppose is less than or equal to epsilon. Okay, suppose that this happens. You know that this happens. Now what can you say about it should be less than or equal to epsilon, because after all GS hat is some function from this class, and I'm telling you that it holds true for every function in this particular class. Okay, so this much I know. So in other words, Rs, let me write it this way. So R of GS hat is less than or equal to RS of GS hat plus epsilon. Okay? Now this holds true for GS hat, but it also holds true for G star. RS of G star minus R of G star should also be less than or equal to epsilon, because G star also belongs to the hypothesis class. So this means that RS of G star is also epsilon close to R of G star plus epsilon. Okay, is this fine? So the risk, yeah.
Why did you assume that R of G hat of S is less than equals to R of G of S evaluated at S?
So this is some function, right? Right? And since this holds true for every G, it should also hold true for GS hat.
Yes.
Huh.
I'm saying that you remove the modulus, so you would assume that RS of G of like you assume that there is an ordering between risk of G hat of S.
Not necessarily, right? So this is just one side of this particular inequality. All right. So this means that RS of GS or R of GS is between RS of GS hat plus or minus epsilon. That's all, right? Okay. So now I know that R of GS hat is less than or equal to RS of GS hat plus epsilon. And by definition, since GS hat is the one that minimizes the empirical risk, RS of GS hat should be less than or equal to RS of G star. Because by definition, GS hat is that function G that minimizes RS, the empirical risk. So now if I combine 1, 2 and 3, I have R of GS hat less than or equal to RS of GS hat plus epsilon, but RS of GS hat is less than or equal to RS of G star. So this is less than or equal to RS of G star plus epsilon, but RS of G star is less than or equal to R of G star plus epsilon. So this is R of G star plus 2 times epsilon. Right? Question?
Sir, RS is the empirical risk and R is the random.
Exactly, yes. The average risk. Right? The main point or the intuition behind this is the following. Right? You know that the empirical risk is epsilon close to the true risk for all functions. Okay, so you think about the risk, right? I mean, geometrically speaking, you know that you take any 2 points, you know that the distance between 2 points is at most epsilon. Right? And this holds true for every 2 points. And distance between these two is epsilon. How far can these two be? 2 epsilon. Sorry, the maximum distance that this can have v is 2 times epsilon. Right? And that's the basic point, that the empirical risk is epsilon close to the true risk for every function, and therefore this is true for the empirical risk minimizer as well as G star. So how far can the true risk of the ERM be from the true risk of G star? Two epsilon. Right? It can't be any more than 2 epsilon. And that's the basic principle. But of course we did use the fact, we also needed this little fact, that the ERM was the one that minimized the empirical risk. Okay, so it is a little, it takes a while to get it conceptually. There's nothing terribly complicated about it. You just have to think about it just a little bit. Okay, so what this basically says is that if Rs of G, in fact, all of this part is kind of completely independent of what we did previously. Right? If I have Rs of G less than or equal to R, is epsilon close to R of G for all G in the hypothesis class, then R of Gs hat, the ERM, is going to be within 2 epsilon of R of G star. If Rs of G minus R of G is less than or equal to epsilon for all G in G, so then the risk of the ERM is going to be, in fact I can say something even stronger, is going to be within R of, or let's just do this, minus R of G star is going to be less than or equal to 2 epsilon. Yep.
To the Chernoff one.
The Chernoff mode, okay?
So
Here? Here?
yeah.
Okay.
This also works for G hat of S, right?
This does not work for G hat of S. The Chernoff bound does not work for G hat of S.
But it works for any G that is.
Any fixed G. Because I want this Bernoulli parameter to remain fixed. It can't be random and dependent on the sample. My G hat S depends on the sample.
If it's working for any G, then G hat.
It's true only if it works for every G. There's a difference between working for any fixed G versus working for every single G in the hypothesis class. Right? This is true. The Chernoff bound is true for any fixed G. Fixed deterministic G. It's not true for a random choice of G, random depending on the data set S. But if this particular event holds for every single G, then it also should hold for the ERM. So in fact, what we have effectively shown is that the probability R of Rs of gs hat minus R of gs hat greater than or equal to epsilon is not less than or equal to 2 times e raised to minus n epsilon square R of g star by 3, but this times the size of g. It's only after I apply the union bound that I can claim that this probability holds for gs hat.
Does this hold for every G?
Which one?
This part.
I mean, it's because it holds for every g that I can claim that this holds for gs hat. So therefore, from the lemma, the probability that the risk achieved by the ERM deviates from the optimal risk by an amount epsilon is less than or equal to the size of g times 2 times e raised to minus n epsilon square R of g star by 3. So the minimum number of samples to achieve a certain epsilon delta error, so if I take this to be delta, then g just take this away. So if I want this RHS to be less than or equal to delta, then n has to be greater than or equal to log size of g by delta. I think 3 by epsilon square R of g star, just by rearranging terms. Okay. So the number of samples that you require in order to achieve an epsilon delta error grows something like 1 over epsilon square times log of 1 over delta. But remember, this also depends on the size of your hypothesis class. So the larger the size of your hypothesis class, the more samples you will require in order to achieve a particular epsilon delta error. So the more rich your hypothesis class is, the harder it is to achieve the optimal risk. You don't know what is the value of R of G star. But still, what I'm guaranteeing is that as long as n is greater than something, okay, I don't know what that is, as long as n is sufficiently large, the ERM is going to output something that is going to be sufficiently close to R of G star with high probability. Okay, so yeah, it's going to be epsilon close to R of G star with probability at least delta. Okay, so maybe let's stop here. Any questions? Yeah.
This was a proof of
That it is pack learnable. So effectively what we've shown is that as long as you have a finite hypothesis class, this is pack learnable. This particular proof immediately will break down if the size of G is infinite. So it's not that infinite hypothesis classes are not pack learnable. We haven't shown that. But this approach does not work if the hypothesis class is infinite. Yeah.
Isn't that G hat of is dependent on the sample?
It does.
So then how about we get it? So it only works for something which is not random.
Yes, but then the point is that I showed that this holds for every G. GS hat is some G.
But GS hat is some other forms that is like.
It doesn't matter. It is some G from script G, right? The main point is that the Chernoff bound doesn't work for GS hat. I can't use the Chernoff bound to derive a bound on this particular quantity. But since I've shown that Rs of G is epsilon close to R of G for every G in the hypothesis class, it should obviously be true for GS hat because GS hat also belongs to the hypothesis class. It's a random function chosen from the hypothesis class, but because this property holds true for every function in the hypothesis class, it should also hold true for a random function drawn from the hypothesis class. It is not, right? So most hypothesis classes of interest are not going to be finite hypothesis classes. Because after all, we have not developed our tool set yet. But even with the tools that are available to us, we can already say something about learning finite hypothesis classes. But this also gives the general idea of the approach that we will use for more complicated hypothesis classes. Okay? So let's stop here.